we see in this reaction is certainly a more difficult reaction than what we saw previously. There is no way that you would be able to balance this reaction simply by inspection. And so the way to balance this is to, first of all, recognize that it's a redox reaction. It's a redox reaction because things are changing oxidation states. I'm going to ignore the spectator ions here because the spectator ions do not participate in the redox reaction part of the chemistry. And so I'm going to eliminate the hydrogens, the potassiums, and actually all of the nitrates. And so that leaves me with this CrO4 2- species. Let's take a look and see if we can't get the oxidation states of the elements here. So if I recognize that the oxygen's a -2, that's a grand total of -8. The potassium is a +1 for a grand total of +2, and this is a zero charged molecule, and so +2 plus 6 -8 is equal to 0. So the chromium here is a +6. Cannot get the 6 in there. All right. The iron in the reactant side, each nitrate is a -1 for a grand total of -2. So the iron here must be a +2 because there's no charge on that compound. So that's a +2. On the product side, we have chromium nitrate 3. So because there's 3 nitrates with that chromium must be a +3, and the iron is with 3 nitrates, and so that too must be a +3. All right, so in order to balance this reaction, what I want to do is to take and break it down into 2 half reactions. Let me start with the first half reaction. And the half reactions are going to involve the things that are being oxidized or the things that are being reduced. We have an iron in a +2 oxidation state, and that is going to an iron with a +3 oxidation state. We have a balanced equation as far as the elements are concerned, but we are missing balancing the charge. The overall charge needs to balance as well, and we can balance that charge using electrons. So I'm going to add an electron to the product side. That's now a balanced half reaction. Is this an oxidation or a reduction reaction? You should be able to tell me that at this point and recognize that this is an oxidation half reaction because the iron +2 is giving up an electron and becoming iron +3. So it's losing an electron. The other half reaction, again, I'm going to cut out the spectator ions. So I'm going to start with the chromium O4 with a 2- charge, and that's going to go to a chromium with a +3 charge. All right, so this looks like it's going to be an impossible reaction to balance because I have oxygens on one side and no oxygens on the other. But in doing this reaction, we can see that there are waters involved in this reaction. We can also see that there's acid involved in this reaction. And so anytime I need those species, I can simply just add them in. So the first thing I want to do is balance any element that is not oxygen or hydrogen. And so the chromium here fits that category. The chromiums, I have 1 chromium on each side, so that's balanced. The next thing you want to do is balance the oxygens, and you balance the oxygens by adding water. So I've got 4 oxygens on the reactants. I'm going to need 4 oxygens on the products, and so I'm going to add 4 water molecules to my product side. Now I've introduced hydrogens, and so that's what I balance last. I have 4 times 2 or 8 hydrogens, and so I can get 8 hydrogens there. Now my elements are all balanced, but my charges are not, and so that's the next thing I need to do. And one way to do it is to take a look at the elements that are changing oxidation states. And so I had a chromium with a +6 way up here. I had a chromium with a +3 over here. And so from a +6 to a +3, if I add electrons to the most positive side, I'm going to have to add 3 electrons to the reactant side, to the most positive side. Right? Now, you should always do sort of what I call a double check on this, and we can do that by counting the total charge on the left and then the total charge on the right. They should be equal to each other. So on the left hand side I have 3 negatives and 8 positives, that's 5 positives, and then I have 2 more negatives, so that would be 3 positives here. I also have 3 positives here, and so the left-hand side balances the right-hand side as far as charge goes. But the other thing we recognize is that we have 3 electrons in one half reaction and 1 electron in the other half reaction. And it turns out that you cannot have differing numbers of electrons. You have to have the same number of electrons. And so the easiest way for me to get 3 electrons on both sides is for me to simply multiply this whole half reaction of iron by 3. And so when I do that, I now get a total of 3 iron 2 plus 2 plus 3 electrons plus 8 H pluses plus CrO4 2 minus going to 3 Fe3 plus 3 electrons plus Cr3 plus 4 waters. And so now we see that we can cancel out things on the left and the right hand side. We've got 3 electrons on the reactants, 3 electrons on the products, and those can all be canceled out. So that leaves me with my balanced overall reaction, and so now I can actually go up and balance the very first reaction that I started with. This is looking a little bit ugly, but I will give it a shot here. It says I need 8 protons, and I can only get those from the nitric acid. So I'm going to have 8 HNO3s. I'm sorry, HNO3. Let me take care of that here. HNO3 plus we have 1 chromate, so I'm going to need 1 K2CrO4. And it says that I'm going to need 3 Fe plus 2. So I'm going to need 3 FeNO3 taken twice. And then my products. I'm going to need some KNO3. I don't know how much of that yet. We'll have to take a look. But I'm also going to need a CrNO3 taken 3 times. And the next thing over is that iron 3 nitrate, so allow me to write on the bottom here. I'm going to need 3 of those FeNO3 taken 3 times, and then the last thing is the water, and according to the reaction right above, I'm going to need 4 water molecules. Alright, so that's a balanced chemical equation with the exception of the nitrates and the potassiums. On the left hand side I have 2 potassiums, so I'm going to need 2 potassiums on the right, and now I should have a balanced chemical equation. One way to check is to make sure that every element is there in equal amounts, but maybe an easier way here is just to count the total number of nitrates. On the left hand side I have 8 nitrates there, and I have 6 nitrates there for a grand total of 14 nitrates. And on the product side, I have 2 nitrates down below here, and I have 3 nitrates here, so that's 5 nitrates. Down on the very bottom, I have 3 times 3 is, 3 times 3 is 9, so that's 9, 10, 11, 12, 13, 14 nitrates. So 14 nitrates on the products, 14 nitrates on the reactants, and everything looks good, other than my very full screen here. Sorry about that. So I'm going to turn this one off, and then on the next one we're going to run through a couple of examples of some other balancing of chemical equations.